Good afternoon. We're going to get started today. I'm Dr. Kay Stefanik, Assistant Director of the Iowa Nutrient Research Center. I want to welcome you all to the spring seminar series, Focus on the Future. For our presentation, we are going to have two presenters who are either current or recent graduate students that have worked on INRC funded research. They will be presenting their experiences on their research as well as their experiences as early career researchers. So just a few housekeeping items before we begin. The seminar is going to be recorded and posted to the INRC website, so you can view it later, share with your friends. For those of you who are in the room, we're going to have a question and answer session after the talks. If you are online, you can either type your questions into the chat bar and I can ask them during the Q&A session, or you can wait until the Q&A, unmute yourself and ask your question directly. So our first presenter today is Adam Buseman. He is currently a water quality planner, project manager 2 for King County, Washington. He earned his Master's of Science in Civil Environmental Engineering from Iowa State University in December 2022. Dr. Michelle Sapir served as Adam's major professor while working on his INRC funded research project, which investigated soil phosphorus in farm potholes and used a blind inlet amended with steel shavings to mitigate phosphorus export. Today, he will be sharing about his graduate research as well as a little bit about his current role at King County.
So yeah, thank you for that introduction, Kay. And thank you to the INRC for having me today, where I'll be talking about a little bit about my research that I did while I was getting my master's, which was reducing phosphorus export in farm potholes, and then using blind inlets amended with steel media. Let's see if I can figure out how to go to the next slide. So here's a little bit of an outline. So I'll give a quick introduction about myself and then jump into the research that I did while at Iowa State, and then highlight a little bit about my current position, and then we can answer any questions. So I grew up in southern Minnesota. I didn't grow up on a farm, but both of my grandparents farmed, and that kind of got me interested in agriculture, and then also just always have cared about the environment. And so that got me interested in agricultural engineering and then land and water resources. You can see a picture on the right there of me in FFA. So I was kind of involved in agricultural activities in school. In 2016, I started my Bachelor's of Science degree at Iowa State and graduated in 2020. From there, I worked at a consulting firm, Bolton and Mink, as a wastewater environmental engineer, designing water and wastewater treatment plants. And then in 2021, that's when I started my master's program in civil and environmental engineering. And then that was about 2 years. And then I was also working part-time at Bolton and Mink. And then after I graduated in 2022 with my master's, I worked full-time in consulting. And then just recently in September of 2023, I moved out to Seattle, Washington to start a job as a wastewater utility project manager and planner with King County, which I'll talk about at the end of this presentation. So jumping into my INRC funded research. So to start out, the map here on the left shows an area in gray, which is the prairie pothole region. As you can see, this region extends as far south as about like where Des Moines is, and then north up into Minnesota, the Dakotas, and Montana, and then 3 Canadian provinces. And then in Iowa, the prairie pothole region is what is referred to as the Des Moines lobe, which you can see here in kind of the gold shading. And this prairie pothole region covers about 173 million acres of land. So now that we know what the prairie pothole region is, let's talk about what actually is a prairie pothole. So prairie potholes are closed depressions that hold surface water. So these were formed during the last glacial retreat, which was the Wisconsin Glacier. And as the glacier retreated, chunks of ice would drop off or break off from the glacier and then kind of become incorporated with the soil. And then over time, these would slowly melt and then form depressions in the land. And then these depressions are sometimes referred to as kettle holes or prairie potholes. And they're typically called or considered closed depressions because the only water loss that these I guess land features have is through infiltration into the soil and evaporation into the air. So there's no really like water outlet. They're just a closed depression. But today, many of these features are drained. And then this figure on the right shows that even though they're drained, many of them still become inundated with water during significant rain events. And now we'll kind of show a little bit what the drainage looks like for these features. And any pothole that is drained is and farmed are considered farm potholes, which is what was the focus of this study. So you can see here we have our exaggerated soil surface with the depression. And then there's the water table, and the pothole can become full and have surface water. And then subsurface drainage was installed, and that can lower the water table and then allow for crop production, and it becomes a farm pothole. And then oftentimes these potholes have what are called surface drainage intakes or Hickenbottom intakes. And then these just allow for faster drainage because water can flow through these surface intakes into the subsurface drainage without having to infiltrate down to the subsurface drainage line. So Iowa's prairie pothole region has an estimated 3.4 million acres of prairie potholes. And this used to cover about, I think, yeah, these 9 counties. So if you put all the prairie potholes together, it would cover these 9 counties. And now 95% have been converted to other land uses or drained. So there's only about a very small portion, 173 million acres. So like a little part of Winnebago County, if you would put all the potholes together that haven't been drained. So a lot of these are now drained or converted to other land uses. So now that we know what kind of prairie potholes are and what farm potholes are, let's talk about like the water quality issues that can come with them. So as I was saying, even with drainage, prairie potholes can become inundated during large rain events. They fill up with water, and the drainage just can't drain the water fast enough. And then a study by Martin et al. Monitored the surface water from these farm potholes, and 2 parameters that were kind of noted in these studies were total phosphorus. And during these inundation events, total phosphorus increased in the ponded surface water. So as the water sat there, the concentration of total phosphorus increased. And then also the concentration of dissolved reactive phosphorus, which is the form of phosphorus that's uptaken by plants, that also increased by 0.46 milligrams per liter during these events. So anytime the water was sitting at the in the pothole, the phosphorus concentrations were increasing. And then with drainage, this then allows the phosphorus to be exported, which can cause toxic algae blooms, especially in the fresh water that's around like Iowa. So any fresh water, like your rivers, streams and rivers, are often phosphorus limited. So any added phosphorus can cause these toxic algae blooms and lead to eutrophication. So if we go back to kind of my pictorial drawing, you can kind of see all the phosphorus, and then the surface drainage intake allows for the export of phosphorus into our natural bodies and then leading to water quality issues. So we had 2 study objectives that I'm going to focus on today. And one was to collect soil samples at different locations within the farm potholes to kind of see how the soil phosphorus concentrations changed throughout the locations within the potholes, and then design and install a modified blind inlet containing iron steel to absorb phosphorus and then hopefully reduce P export. So our study area was 2 potholes located south of Ames. So one pothole was referred to as Bunny, which you can kind of see if you look kind of sideways, that looks like a bunny with the ears here and the head here and the tail here. So I think that's kind of cool. So that pothole was about 13.2 acres. So the red shading, and then its watershed is about 101 acres. And this pothole has 2 surface intakes with subsurface drainage. And then the other pothole, the pothole where we installed the modified blind inlet, it's about 6.4 acres. So about half the size of Bunny, and its watershed is 24.2 acres. So quite a bit smaller than the watershed of Bunny. But since they were right by each other and then in the same field, it kind of allowed us to still use it as a comparison site, even though they weren't exactly the same pothole. So what did we do for soil sampling? Here you can see where we took samples. So we took samples at the bottom of the pothole, which are represented by these orange pins. And then we also did middle of the pothole, which are the red pins. And then the outside of the pothole, which is along the delineated boundary of the pothole. And then also took samples outside of the pothole. So there were 4 sampling locations. And then at each location, we took about 4 samples. And then we sampled down to a depth of 1 foot, but then divided the sample in half. So we had 2 different sampling depths of 0 to 6 inches and 6 to 12 inches. We analyzed 4 parameters of these soil samples. So we sampled the wheat-bray phosphorus, which is usually in Iowa referred to as like the soil test P, and usually referred to as like the plant available phosphorus. And then the strong bray phosphorus extracts a little bit more phosphorus out of the soil. So it's a stronger extractant and results in a little bit higher concentrations. And then we also looked at total phosphorus and then soil microbial biomass P phosphorus. So getting into the results of this, one finding with the wheat-bray phosphorus is that it's higher at the top of the soil compared to the bottom, 6 to 12 inches. So it's about 2.6 times higher across all sampling locations than at the top of the soil surface compared to the 6 to 12 inch. And this makes sense because if phosphorus is applied as a fertilizer, it takes a while for it to move through the soil profile, and then also it may not be very mobile through the soil profile, so it kind of just stays near the top of the soil surface. And then another interesting finding was that there was more wheat-bray phosphorus at the bottom of the pothole, so right kind of where your surface drainage intakes would be, compared to outside locations. So as you can see in this chart, as you work your way out of the pothole, the phosphorus concentrations were decreasing. There was a lot more near the bottom, so a lot of accumulation of your soil test P near the bottom of the pothole. And on average, it was about 8.7 times higher at the bottom of the pothole compared to outside of the pothole. And then since wheat-bray phosphorus is oftentimes, again, referred to as like your soil test P, the ISU extension has recommendations for wheat-bray phosphorus. And as you can see, a lot of the bottom and middle locations within these potholes were in the very high to high range, which is also kind of surprising too, because we took these soil samples right after a corn harvest. So you would think that you have a depletion of phosphorus, but these show that there was still quite a bit of phosphorus in the soil even after the corn had been harvested and uptaken the phosphorus. So we did the same thing with strong bray phosphorus and saw generally the same trends of more phosphorus being at the bottom of the potholes. You can see the decreasing trend as you work towards the outside. And then since this is a heavier extractant, it got more phosphorus out of the soil, but generally saw the same general trend. And then, as I mentioned, we also looked at soil microbial biomass P, but we didn't really find any trends with this data, which suggests that microbes and phosphorus are not really affected by the location within the pothole and might not be playing that big of influence within these land structures. So now I'll jump into the design of the blind inlet. So the initial site conditions, you have your surface drainage intake here. And then what we did is we popped off the surface intake and then excavated down to just above the subsurface drainage, and then lined the excavated bed with geotextile fabric, which you can maybe see is this orange dash line here, and then installed a collection manifold to allow the water to drain into the drainage line. And then this pit got filled with clean pea gravel and mixed with iron steel shavings. It was about 8% by weight, so it ended up being about 2 tons of iron filings used. And then we capped it with a geotextile layer on top, and then used a sand gravel coarse layer on top just to kind of protect the media bed. So that way soil and sediment weren't clogging the gravel and steel shavings. And then this wouldn't be typical of a normal structure that would be installed, but we had 2 water control structures that just allowed us to take grab samples and monitor the modified blind inlet. And then here's a top view so you can see the dimensions. It was a 15-foot by 15-foot excavation, and the collection manifold was 10-foot by 10-foot and had the perforation holes to allow for the drainage. And then the water control structure number 1 would allow us to collect our effluent from the blind inlet. And then once we collected our effluent, the water could flow back into the subsurface drainage line. So then here are just kind of some pictures of the actual construction. So there you can see the geotextile fabric being placed in the pit, and then the collection manifold being installed. And then here's where the steel shavings and gravel were being mixed together in the back of a truck bed. And then they used an excavator to kind of try to mix it around. And then when it was actually in the bed, you can see a lot of the iron filings were actually clumping together. So in the future, we'd recommend trying to get the iron filings shredded before being delivered, so that way you can have a more uniform mix. But they raked them apart and tried to get them evenly distributed as possible. And then there's the top geotextile, again, to kind of protect that media bed. And then the sand cap, and then the completed blind inlet with the 2 water control structures for monitoring. So if we go back to the little picture, it kind of looks something going from this to that. And then we could take grab samples of your effluent or influent of the blind inlet, which would be your surface water. And then the effluent would be here. And then we also did take grab samples of just the subsurface drainage water. So why did we choose iron filings? So the surface of iron oxides, so of your iron, once it rusts, can have a positive charge due to the oxygen ions, and then dissolved phosphorus has a negative charge, so the dihydrogen phosphate and hydrogen phosphate has negative charge. So then once you have your rust on the iron surface, it can perform what's known as like a ligand exchange and create a bond and bump out one of the water molecules and replace it with one of the oxygen molecules on your phosphate. So now looking at the data from monitoring, so this blind inlet was installed in 2021, but 2021 was kind of a dry year, so we didn't actually have any events that allowed us to sample in 2021, so we didn't have any data in 2021. And then in 2022, there were 4 events kind of in the spring, early summer that had inundation at Bunny, and then 3 events at Walnut, which was the pothole with the blind inlet. So there were 3 events that allowed us to kind of monitor the blind inlet. And here you can see the results from the dissolved reactive phosphorus and total phosphorus. So the first event was just 1 day, and that was this line here. And then you can see we only were able to collect 2 samples, even though the events were for 4 days and 8 days. This was due to, for some reason, the blind inlet stopped flowing after like that second day for the events that were longer than 2 days. We're not exactly sure why, but we think that the sand in the sand cap layer that I talked about, it may not have been a uniform sand. So the smaller sand particles likely sorted and filled in all the gaps and created a surface with very low hydraulic conductivity. So then water wasn't able to actually flow into the blind inlet. And then this was kind of evident by just walking on the surface of that. It was felt like rock hard when you would walk across it. So we're thinking that's what happened, but we're not totally sure. But the results were still promising. The ones that we did, samples that we were able to collect, we saw that dissolved reactive phosphorus, the steel media retained and removed about 82% of the influent dissolved reactive phosphorus. And then it also prevented about 61% of total phosphorus from being exported. So the key takeaways from the study were that soil phosphorus levels are high near the bottom of farm potholes. So we really need some sort of best management practice like these blind inlets to kind of help control and prevent the release of phosphorus into our waters. And then the modified blind inlet that we installed can retain about 80% of the influent DRP and filter out about 60% of the influent total phosphorus. And just that was like preliminary results. So obviously we'd want more data to kind of back this up and support that, but it does show promising results. So that was my research, and now I'll go a little bit into my current position. So I moved out west to Seattle, and now I'm working with King County as a wastewater utility planner. So a little bit about the wastewater treatment system out here. So there's 5 treatment plants that the utility is responsible for. There's about 3 main ones. So West Point service area is this pink area, and Seattle is like right here. So West Point services this pink area, and then the South Plant services this large area, and then Brightwater has this smaller service here. And then there's also 2 other tiny wastewater treatment plants, one right here, and then one on Vashon Island. So in total, the entire system serves about 1.9 million people and treats an average flow of about 178 million gallons per day, with a peak flow of 720 million gallons per day. So pretty significant, and with it being kind of rainy in the winter, your peak flows can be kind of high, especially due to aging infrastructure of the underground conveyance pipes. And then, so what I'm doing is I'm helping develop plans for maintaining treatment capacity. So as the area continues to grow, the population continues to increase. So just developing long-term treatment plans for how they're going to expand, and then also developing plans for meeting regulatory requirements. There's the Puget Sound Nutrient General Permit for reducing nitrogen export into Puget Sound. So working on how we can optimize nitrogen removal at the plants and developing plans for that. So overall, I would just say like this INRC funded project that I just talked about has really helped me gain like technical writing skills that I'm using a lot to develop the plans, as well as just data analysis, do a lot of data analysis to come up with the data that we're using in our treatment plans, and then just also so I know I'm not technically in a research heavy focused job, but my master's work has definitely helped me get prepared for the job that I'm currently in. So now I'd just like to acknowledge all the people that have helped with my research project. So Doctors Michelle Sapir, Amy Kalita, Joe Charbonnet, Chad Penn with the ARS, and then Leanne Long, and then all the water quality research lab members, all the undergrads that helped with data collection and water sample collection. And then also thanks to the INRC for funding this project. If you want to know more about my project, we do have a paper published with the Journal of the ASABE. So with that, I don't know, I think we're going to save questions for the very end, but that's what I had.
Thank you for that talk. I think based on time, we are going to move on to our next speaker. Do you want to start getting your PowerPoint up and I'll introduce you? All right, would you mind stop sharing your screen, Adam? All right, thanks. All right, so our next presenter is Gabrielle Myers-Bailey. She is currently working on her PhD in agricultural and biosystems engineering with Dr. Raj Raman. She has been involved with the Regenerating America's Working Landscapes to enhance natural resources and public goods through perennial ground cover project, specifically examining the effects of perennial ground cover on water quality. After graduating this spring, she will be continuing her work on water quality with the United States Department of Agriculture.
All right, hello everybody, I'm Gabby, and today I'll be presenting on our INRC supported project where we're studying the water quality impacts of perennial ground cover in tile drain corn production. So starting with a little bit of about me, I was raised in Underwood, Iowa, a small town in southwest Iowa, sort of near Omaha, Council Bluffs. I grew up in a generationally Iowa State family, so it made sense for me to come to Iowa State for my undergrad. I started my undergrad as an open option major, completely open option. I don't know, I think I just closed my eyes and pointed at something and decided on biosystems engineering. But I had a really great experience and decided to stay in the department for my graduate work. So I'm hopefully, if everything goes well, wrapping up my PhD this semester. My major professors are Raj Raman and Dan Anderson. And then also on the project that I'm presenting today, Ken Moore in the agronomy department is also on that. And like Kay said, I'll be starting as a research hydrologist in a postdoc position with the USDA Agricultural Research Service in their vegetable crops research unit at UW-Madison. So in that work, I'll be working on water quality and soil projects related to cranberry farming. So a little bit different, but still in the water quality realm. Why water quality research? So aside from the fact that it was what my major professors were doing, I really enjoyed working on water quality research. I grew up connected to agriculture through my grandfather, who was a corn, soy, hog farmer in northern Iowa. And then I spent a lot of time as a kid and still do on various lakes in Iowa and Nebraska. So I really enjoy getting the opportunity to work on things that I really think can improve those recreation spaces and preserve them for later, and also improve our drinking water quality as well. So I still go up to Okoboji all the time. That's a picture from this summer. Not looking that great, wouldn't want to drink it. We still swim though. So many of you know this, but in the Corn Belt, we're characterized by a lot of corn and soybean production, and that system results in us having long periods of bare soil between the annual row crop growing periods. So those fallow periods are associated with a lot of environmental consequences, but especially soil and nutrient losses. And those soil and nutrient losses lead to drinking water contamination, local and downstream eutrophication and dead zones, and then of course land degradation from the loss of that topsoil. So we know that we need scalable solutions that fit into our current agricultural production system in order to improve on those negative outcomes. And then a common solution to those is cover crops. If you're not aware, with cover crops in the Midwest, typically it's a annual cover crop that's planted in opposite seasons of the cash crop. So the management typically looks like what I have shown on the screen here. We plant the cover crop after we harvest the cash crop in the fall. It starts to establish and provide soil cover throughout the winter and early spring when the cash crop isn't growing. And then farmers need to terminate that cover crop with an herbicide application usually at or before the planting of the next season's cash crop. So despite the fact that cover crops have proven to be very effective in environmental improvement and government incentives available, adoption rates are still really low. 5% may be generous with how much they are used in the Corn Belt. And we think that that is due to the fact that the times between harvesting your cash crop and planting your cash crop are already super busy. And so farmers might want to use their good weather days to manage the crop that's actually making them money and not be worrying about a cover crop. That belief is also supported by what different social science researchers have found in farmer surveys. This first one I'm showing, they did a survey of non-cover crop adopters, and the top concern identified in each survey was the time and labor required to maintain and manage a cover crop. This other survey found that farmers identified the difficulty in the timing of those management practices with the cover crops. Just like I said, planting the cover crop in the fall and terminating it in the spring, those are really busy times for farmers. So the solution that I'm covering in my presentation is the perennial ground cover or PGC system. So this is different from annual cover cropping because we use a perennial plant species planted between rows of the cash crop. It provides year-round soil cover, and the ideal PGC would be complementary to the cash crop. So sort of like in this soil profile that's shown in the picture, shallow rooted, so it's not competing with the corn for water or nutrients. There's several benefits to the system, some that we've already shown and some that we anticipate. One being lower cost and complexity in management compared to annual cover crops. Of course, reduce soil erosion because you have soil cover throughout the entire year. And then today we'll be focusing on decreased nutrient export because you have a plant growing all year to take up the excess nutrients. So in the establishment year of perennial ground cover, it'll look pretty similar to an annual cover crop. Typically, you'll plant the perennial ground cover after the harvest of the cash crop in the fall, but that's kind of flexible based on the weather. You could also plant it in the spring. If it establishes really well, we need to suppress the perennial ground cover chemically just to turn it brown for a while, because corn will have a significant yield reduction due to its shade avoidance response if it senses some green plants around it. In the later years, since it's a perennial plant, you don't need to replant it, so we get rid of that extra step. And then suppression, even if you still have to do that, it's an extra step, but instead of being pre-cash crop planting like in the annual system, we move that to post-cash crop planting, which tends to be less busy for farmers and maybe more easy for them to get the labor required to do that. So in this project, our main goal was to evaluate the effect of perennial ground cover on nitrogen export. But we also, of course, kept track of yield, some soil characteristics like moisture content, aggregate stability, and had some erosion pads on the field. And then we also kept track of total reactive phosphorus in the tile drainage as well. And then we're comparing how the perennial ground cover system does to conventional corn production and a couple different annual cover crop systems. So the study took place at the Northeast Iowa Research Farm, which is just right outside of Nashua, Iowa. We have 36 plots total. 12 of them are in the study that I'm talking about today. It's in randomized complete block design, and we have each treatment in 3 different plots. So at the farm, we have a specialized drainage system where each plot has its own subsurface drainage. We collect the center tile line for water quality and flow analysis, and we don't collect the outside ones to prevent mixing with the surrounding plots. So we have 4 treatments that I'll cover in this. The first one is the control. So in this case, we have continuous corn, so we're not rotating it with soybeans in this case. We get 200 pounds of nitrogen per acre through fall injected swine manure, and it also gets strip tilled in the fall. The perennial ground cover treatment in this study uses Kentucky bluegrass as the PGC. Otherwise, it's the same management as the control, where we get 200 pounds of nitrogen, and we use swine manure and strip till. The next 2 treatments are interseeded cover crop treatments. So in this case, they're not a typical cover cropping system. Instead of planting them after the fall, or after the cash crop harvest in the fall, we plant them after the corn is already growing. So in early to mid-June. So in this case, you don't have to terminate them. They just die over the winter, hopefully. Sometimes they reseed themselves and show up again. But we have 2 different treatments of interseeded cover crops. The first one that I have on the screen now is in our standard row width. So the same row width as is typical in Iowa, which is 30 inches, and that we use in the control and the PGC. And then we have another interseeded cover crop treatment where we have twin rows of corn, and then they're spaced out in sets of 2. So you have 52 inches of space between sets of twin rows. And this is so we can get more sunlight down to the cover crops so they can establish better. They get planted at the same density as the other plots. So the same number of corn plants, they're just spaced out differently. And we got a lot of cover crop growth here. You can see in the pictures in the fall, we have a lot of green. Okay, I'll get into the results for our 3 field seasons. I'll start with precipitation. Precipitation was not really on our side in this project. And every year we had below average precipitation. In 2021, which is the tan line on this plot, it was really dry throughout the spring and early summer. And then we got a lot of rain in the fall, and it became like an almost average year. But the timing of it is sort of opposite of what happens in Iowa. Normally we get more in the spring and less in the summer. We had the opposite in 2022. It was pretty normal in the spring and then just pretty dry in the fall. 2023, it was just very dry, but it started out really early spring, normal, and then it just basically stopped raining for the rest of the year. So from our gauges at the farm, you can see that we were 9 centimeters below normal during the growing season. In 2021, 11 below normal in 2022, and then we got less than 50% of normal precipitation in 2023. So the timing and the amount sort of varied throughout the years. And this is what our tile flow looked like. So tan line again for 2021, you can see that we really didn't get any flow until late August, and that's when we ended up getting a lot of rain. But that meant for the rest of the time, we weren't getting much for water samples. In 2022, we had a lot of flow comparatively in the spring, and then it just stopped flowing. And then in 2023, the tiles didn't flow after July, and before that, it really wasn't that much. So this is average for all the plots, but there was really no treatment effect here. Similar for all the treatments. The average for the 3 years was 5.3 centimeters. In previous studies for these plots, normal is between 10 and 15. So pretty low. With that dry conditions, we had a lot of trouble getting our perennial ground cover to actually establish well. So like I said, 2021 was really dry in the spring. We planted the grass in fall of 2020, and then it proceeded to be very dry until the next August, essentially. So it didn't grow very well that first year. We didn't have to suppress it because really you had to like look with a magnifying glass to see it. In 2022, we had some wetter conditions in the spring, and it actually started to look okay. You could see in one of my pictures, I've got some strong rows of perennial ground cover. Still, it was pretty variable throughout the plot. We'd have some places with a lot, some places with not a lot. We did suppress it that year, and it suppressed well, which was good because in some other studies they have issues with suppression. But what was bad is that it didn't come back really. So We replanted it again in 2023 when it was looking like it was going to be wetter. And essentially after we planted it, it stopped raining again. So it really didn't establish very well. For corn yields, you can see that in 2023, it was the lowest, which makes sense because I said we got less than 50% of our normal precipitation that year. In each year, the wide row interseeded cover crop treatment was lower than the other three. This makes sense with the way that we apply the manures on 30-inch and 30-inch spacing. And so for these plots to get the nitrogen, the corn roots would have to grow laterally to go get the nitrogen. And when it's dry, normally corn roots go down deeper instead of laterally to look for water. So the combination of how the manure was applied and the dry conditions just really didn't help out that treatment. But the other three treatments, all the treatments that were in 30-inch rows, did not differ from each other. Here I'm showing the nitrogen concentration in our tile drainage. So in 2021, when it was really dry, our concentrations looks great. Like that would be awesome. The EPA drinking water standard is 10 milligrams per liter, and we were definitely much below that. And that year, the wide row interseeded cover treatment was significantly lower than the other three. But the other three were similar to each other. When we look at the data overall, the wide row interseeded cover and the perennial ground cover are around 25% lower on average than the control, and that is statistically significant. So that's good. Like I said earlier, we did measure other things. So we kept track of the phosphorus concentration in the tile drainage, and we calculated loads. We didn't see much of a treatment effect there, so I didn't include it here. Same with nitrogen loads. There wasn't a treatment effect, although we did have lower concentrations in the PGC and wide row interseeded cover, like I said. It didn't translate to a lower load. We kept track of soil moisture content. It told us that the soil was very dry. We put out erosion pads, and we didn't see much of a treatment. I mean, it didn't rain that much, so like you don't see a lot of erosion, especially on very flat plots like we have there. We measured aggregate stability, which could be interesting if the cover crops are building organic matter and improving the aggregate stability. But over the time scale that we had, there wasn't a big difference between them. All of them were very stable, but not much of a treatment effect there. We also buried strips of cotton t-shirts and found that it's really related to how much it rains. In the first year, we left them underground for a long time, and still they didn't decompose that much. And then the second year, we're like, okay, we got to leave them longer. And then it rained, and by the time we dug them up, they were all gone. So like maybe we just got to figure out the exact amount of rain you need to get to dig them up. But really, everything in this study is very related to the amount of precipitation that we got or didn't get. So just to summarize, the yields were similar in all of our standard row treatments, but the wide twin rows, we had reduced yield in every year. In that wide row treatment, the cover crops were looking great. There was a lot of bugs on them, bees, moss, everything, and we had lower nitrogen concentrations in the drainage water, but that was accompanied by a really significant yield loss. And then even though we had really weak establishment in the PGC system, we did see a lower nitrogen concentration, statistically significant, so that's good. Maybe in the future, when we figure out how to get it established better, if we have access to irrigation, we'd expect that that would be enhanced. We'd see an even lower nitrogen loss. And then, yeah, like I said, the variable timing and just the lower than average precipitation overall really affected those nutrient loads and their concentrations and gave us a lot of trouble with getting the grass established. In the future, at these plots, we're going to look at other PGC species that may be established better under different conditions, and also get it integrated into a corn soybean rotation. So the professors on this project are Dan Anderson, Raj Raman, and Ken Moore. I got a lot of help from fellow graduate student Philip Roxon in getting samples and analyzing them, as well as several undergrad researchers. The Northeast Research Farm staff and superintendent handled the water sample collection and all the farm management. And then the Water Quality Research Lab and Leanne analyzed all of our water samples. That was really helpful. In addition to the Iowa Nutrient Research Center. It was supported by the Iowa Pork Producers Association, Region PGC grant, and the Data Fusion Research Traineeship funded me for a year. All right, I could take questions.
Thank you so much for that. I think we can open up the floor to questions for either Gabby or Adam. Are there any questions in the room?
Oh, I have a question for Adam, if he can hear me. Adam, what were your phosphorus concentrations from that drainage main without the intake, the one that you had like that second control structure on? Were they, yeah, kind of what were those levels? Do you remember?
I don't remember off the top of my head, but they were definitely lower than like what we were seeing on the surface. I remember, I don't have the numbers off the top of my head, but both at Walnut and Bunny, they were lower in the main tile, subsurface tiles compared to the surface. Does that kind of answer your question?
Yep, that does. Okay, not to dominate it, but I have a question for Gabby. Your bluegrass did it, and you may have said this, and I was concentrating on something and spaced it out. I know it was so hard to establish. Was it getting any better as we went to like in 2020, like 2023 before it got so dang dry? Or
In 2022, it was looking kind of good, and in some places. If I'll go back to it. Like this picture in the middle, like we had places that looked pretty good.
okay,
And then like we suppressed it to avoid the shade avoidance response, and then it didn't come back as well. I think maybe if it would have rained more after, maybe it would have come back stronger, because also 2022 we had the wet spring and dry summer. So
and that remind me, I should know this too, but that system stayed in there. So
yeah, and then they're also adding the Poa bulbosa.
also,
Yeah, so that's a PGC that it self-suppresses, so you don't have to do the suppression. And maybe it's a little bit easier to establish than the Kentucky bluegrass. Has a little bit less of a water requirement.
And I'm not seeing any questions online. Have you got anything now?
no, I have.
Okay, well, I have a question for Adam. With the steel filing, well, actually kind of two questions. With the steel filings, are those something that need to be replaced after a set amount of time? And are there any kind of chemistry related concerns that might cause maybe pulsing of phosphorus out of that system or release of phosphorus?
Yeah, so I guess can you repeat the first question? I know the second one was like concern. So sorry, I got distracted.
Oh, it's okay. Do the steel filings need to be replaced after a set amount of time?
Okay. Yeah, so we've done, well, I would say I haven't done, but Chad Penn has done some like looking at this, like kind of how long they could continue to absorb the phosphate. And it looks like at least like depending on like your loading, it could last at least up to like 5 years, if not more. So eventually there is a point where like all your sites on the iron filings would become like saturated or full, but it all depends on like kinetics and what your loading is. So obviously if there's more phosphorus, the sites are going to fill up faster. And then the second question about, yeah, if there's like kind of a release of phosphorus. So that is something that probably needs a little more research into it, but the ligand exchange like creates a covalent bond, and that is a pretty like strong like bond that holds the phosphate pretty tight and isn't going to leach, but it is pH dependent. So once you get out of kind of where like kind of more neutral to acidic pHs, you can lose your phosphorus. So that's kind of another thing that we would want to like continue to study with these systems, is if like at what pHs does it start I guess releasing the phosphorus. And a lot of times that can happen with anoxic conditions, is that your pH changes. But with like other studies that we've looked at, it hasn't actually like seen any release in the field, but obviously we would want more data to like support that, I guess. So does that answer your question?
Yes, thank you. Any final questions?
Yeah, so once the PGC is established properly, like say we get a good boundary plan, how often do you plan like think with forever or you?
Yeah, I mean, I think hopefully never.
Can you repeat the question? for
Yeah,
those
the
out
question was, how often would you need to replant a PGC if they establish well? I think, yeah, maybe never. There's some plots that are older than this project in Boone that have been around, but they haven't been suppressed every year. So really like the managing it exactly how we want it to, I don't think we fully know. But I think ideally not.
And I think, are you also looking at pure clover, or has that been kind of ruled out?
There might be some of the people on our project looking at carrot clover, but I'm not involved with it. I think it's a little bit harder to suppress, actually, is what they found. It's harder to turn it brown, and then if you can't get it suppressed, you get a really significant yield reduction.
Well, I'm not seeing any questions online. So thank you again to both of our speakers. Great job, both of you.
Thank you, everyone.
Thanks, Adam.
Thanks,